Good afternoon. My name is Silva. I'm from the IJUP09 Southport, the Unidade of IJUP09, and I'm here to talk to you about femtosecond light pulses. So, what's so special about these really short light pulses? Basically, they're pulses of light with durations of the femtosecond. That's the minus 15 seconds. And if you put things in perspective, 1 femtosecond is to a second, that's 1 hour, is to the age of the universe. So basically the idea is that 1 femtosecond is a really short time. And the other interesting characteristic is that you have big energy densities of the orders of terawatt or terawatt. Basically that's a lot more than what all the world's power plants are producing right now, that's 50 terawatts. So you have light vehicles, very short light vehicles that is able to give a very high level of power intensity, but only for a very brief duration of time. And another thing is that they are produced in ultra-fast lasers, and I'm not going to be talking about the production of these impulses. So, an interesting characteristic. How do they interact together? For example, if you try to do pulse with longer impulses, with 9-second impulses or with a higher duration, you get very bad effects. For example, there is coming out of the material. There is so much energy. The duration of the impulse is so big that there is too much. The temperature rises so much that all the material around your hole melts or is burned. This is really not good for example, biological tissues. If you take a femtosecond pulse, the impulse is so short that there is no time for those bad effects to happen. For example, I have here 2 pictures. One is a 9-second pulse, and the other is a femtosecond pulse, much more perfect. So this is used in various applications nowadays. For example, in eye surgery is made in femtosecond pulses. There is very interesting research in neurosurgery. Some researchers have a setup that can take 2 neurons and break only the connection between them. That's important to study some neurological diseases. And for example, in cancer research, there are also other researchers that are able to destroy just one cancer cell, and leave all the other healthy cells around the cancer cell intact. Another application, very interesting, is femtosecond micromagnetic that has many applications in the industry. And I will not be able to explain how it happens, but you can but you can see that it is possible to produce very detailed shapes with a very small size. And to put things in perspective, a typical bacteria has a size of 1 to 10 micrometers. This bulb has something between 10 to 20 micrometers. So we're making very detailed shapes at the size of the bacteria. Well, and then there's many more applications of these femtosecond pulses from areas from metrology, nuclear fusion, health, and especially fundamental research in physics. So where does our work come in the middle of this? Basically, each of these femtosecond pulses has a certain energy in them. And the higher this energy is, the more useful for applications these pulses are. So what we're trying to do is basically generate pulses, femtosecond pulses with something like 6 femtoseconds with much more energy in them. So there are 2 approaches to this problem. One is some kind of pulse amplification. That is not the approach we're doing. We're working with pulse compression techniques. So basically, with pulse compression techniques, you take a much broader pulse with a lot of energy in it, and you basically shorten it and get a much smaller pulse in that. So right now there are 2 main femtosecond pulse compression techniques. One is called hollow fiber, and it was demonstrated in '96. It's a very well-studied technique. It has some known limitations, however. It has what I want to talk about is self-compression by filamentation. It's a very recent technique, only demonstrated in 2004. It solves some of the limitations of hollow fiber, but it is not yet very well understood. So there is much work to be done in this area, and that's what we're trying to do. So, what is roughly self-compression with filamentation? You start with a femtosecond laser that produces, in our case, for example, it's pulses with 27 femtoseconds duration and 1 millijoule of energy per pulse. You focus the pulse in the first right iron chamber, and the fact that you focus this pulse with so much energy in a so small area, in a very small volume, produces an ionized filament. A filament is the same thing that happens in a lightning bolt. Basically, all the gas is ionized. So you get this extremely interesting and beautiful phenomenon to watch. And when the pulse comes out of the ionized filament, basically it has been self-compressed. It comes out with a much shorter duration, but with roughly the same energy. So what happens, and I'm not going to be able to put this in detail, it's that there are many non-periodic phenomena in the ionized filament that make the pulse self-compressed. So there's certainly a lot of potential in this technique to self-compress the pulse. So our approach, we need to do two kinds of studies. One is the experimental study in the lab, see which conditions generate self-compression, see which do not. And then we need to model everything in the computer to see if we are having see if we really understand and make sure we know what is happening. If we don't know what is happening, well, we have a big problem. So we don't yet have results. These studies are still going on. So my conclusions are that femtosecond pulses have many applications that are very interesting tool nowadays. They have applications from health to fundamental science to industry. We are working on this, and self-compression